Okay, so today we are going to start our unit on radical functions. Radical is a fancy name for a root. So we are going to look at root functions in this unit. And the first thing that we're going to talk about with these guys is their graphs. So before we get into the graphs of those radical functions, I want to do a little refresher using some graphs of polynomial functions. So we just finished 2 units on polynomial functions. We are very familiar with vertex form and graphing quadratics. So we are going to take a look at some of those as a refresher. So as I take a look at my options up here, I know that all of these should match to a graph down here. We've got more graphs than we have functions, so we'll have some extra graphs. But let's start with our x squared graphs. We did a lot of work with x squared functions, with quadratic functions. So let's take a look at our x squared graphs. This A is an x squared function, 2x squared. Its vertex would be where? Where's the vertex going to be for this? 0. Yeah, our vertex is at 0, 0 at the origin. So that would have to be number 5 based on its vertex. And then that 2 in front tells me we're going to go up 2 and out 1. So number 5 is function A. Our other x squared graph would be D. Where's our vertex for this thing? Where's our vertex for D? 1, 1. D. 1, 1. So that would be here. Here's our other parabola, and that's not the right vertex. So this would have to be D. And then those are our only x squared functions. So 2 is a parabola, but it doesn't have an equation. So we'll write the equation for this one. This would be y equals, our vertex is at 0, 1. We're opening up. I go up 1 and out 1 for that first nice point. So this would be x squared plus 1 for our function there. If you wanted to, you could put x minus 0 in parentheses squared. And then our other functions are x cubed functions. So another type of polynomial here. We can see from function b, what information do I know about b? Cubic functions don't have a vertex, but if I see something in parentheses with x, and it's not vertex form, what is that telling me about? Another key feature of a graph. August through November, we worked on these functions. So if I see something in parentheses with x, what is this telling me about the graph right here? I have an x-intercept. Thank you. Where do I have an x-intercept? At 1. So I'm looking for a cubic function with an x-intercept at 1. Which of these would that be? 4. Yeah. And I would expect, because it's got that 3 as an exponent, I would expect cubic behavior there, which is what I see here. So 4 matches with B. C is the last function that we're given. So C's got to be either 3 or 6. The only additional piece of information I have is this 1/2 in front. So for a cubic function, if I don't have anything in front, to get from that sort of center to the next nice point, I'm going up 1 and out 1. What do you think that 1/2 is going to do? With the 2 in front of our x squared here, it stretched it out. So what do you think the 1/2 is going to do? Yeah, kind of smash it down, kind of widen it. So which of these 3 or 6 is a widened version of that function? 3, yeah, this is C. And then for 6, this is not widened, but it is flipped, right? Instead of going up and out, we're going down and out. So this would be y equals negative x cubed, since we flipped it upside down. So these are functions that we have seen before this year, right? This is Algebra 2 stuff that we saw here. Now the quadratics we also saw in Algebra 1. But this is a refresher of stuff that we've seen more recently. If we turn the page, we've got the start of our radical functions. Okay, so I want you to remember that transformation stuff. Where's the vertex? Where are the x-intercepts? Is it stretched? Is it compressed or flattened? That's going to come back into play in a couple minutes. But we're going to start our radical functions by taking a look at the parent graphs for square root of x and cube root of x. These are the two that we're going to focus on in this unit. Square root of x and cube root of x. Okay. So the first thing we're going to do is make a table and talk about what that function is going to look like. So we'll get into using those transformations here in a little bit, but we're going to start by just making a table. So we have some values for x here, and then our function is to take the square root of those values. So if we take the square root of -4, what do we get? 2i. Can I graph that? 2i? No. So I'm not going to get a point from that. How about if I take the square root of -1? One I. Yeah, 1i. Can I graph 1i? Where I have these imaginary y values, I'm not going to get points on the coordinate plane, not on the real coordinate plane. How about the square root of 0? 0. Can I graph this now? 0, 0? Yeah, that's a point on the plane. What's the square root of 1? 1. So I'd have the point 1, 1. And then my next x value is 4. Why do you think they skipped 2 and 3? Yeah, they're not nice roots, right? Square root of 2 is not a nice number. Square root of 3 is not a nice number. So our x values are things that are going to give us nice square roots. Square root of 4 gives me 2. So we have the point 4, 2. And then we skip 5, 6, 7, 8 because they don't have nice square roots. So when we've made tables in the past, we tend to pick just a list of x values in order, no skipping around. As we're working on these square root and cube root problems, keep in mind that you don't have to pick every x. You can pick x's that are going to make your work a little easier. So that's what we've done here. So for our final x value, square root of 9 gives me 3. So I have the point 9, 3. So as we look at our graph now, I'm going to plot these points. We have a point at 0, 0. We have a point at 1, 1. We have a point at 2, 3, 4, 2. And 5, 6, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3. Just off our graph there, but 9, 3. And I'm going to go ahead and connect these points. Square root graph, hopefully you remember seeing this in Algebra 1, is our one graph that we look at where we don't put arrows on both ends. A square root graph has, if you had me in Algebra 1, what I called a terminal point, that sort of end point right there. It's sort of like the graph version of a ray from geometry. Remember in geometry, when we talk about lines, we talk about something that goes forever in both directions. And when you had a ray, it had that endpoint, it went forever in only one direction. A square root graph is kind of like that. So we have this sort of key point or this end point at 0, 0 for our parent graph, and then we go forever only in one direction. We're never going to get anything back this way of our key point because we had imaginary y values there. Okay, so we will see graphs where this key point is shifted all over the coordinate plane, and that's okay. But when we talk about that key point, the graph is never going to go back from our key point. Okay, after we flipped or changed that orientation or moved it somewhere, that key point is going to be sort of like an end point. So I want you to notice that our key point for our parent graph is at 0, 0. So we can use that as our reference point. And then to get to the next nice point, we're going up 1 and out 1. So that can help us to graph with any transformation. So our next nice point is at 1, 1. And then again, because when we take a square root, we're going to have this sort of endpoint because of those imaginary potential y values. That means that our domain and our range are restricted here. So the domain for our parent graph, remember domain are those x values, is going to be any x value greater than or equal to 0, right? This is the smallest x value I can have for my parent graph. I can't have negative x values because if I have negative x values, when I take the square root, I get imaginary y's. That also means for our parent graph, our range is restricted. So range, remember, are those y values. Our y also has to be bigger than or equal to 0. Since we start our x at 0, that means our y is also going to start at 0. And again, we will look at graphs where we maybe throw a negative in front or we shift it left or right. So these features are for our parent graph specifically. They'll change as we change our function, but it gives us a starting point. It gives me some sort of landmarks to look for to be able to graph any other square root function. And then we're going to talk about the same thing for cube root functions, okay? So a square root, when we were taking the square roots, we were looking for what number multiplied by itself would give me that. So square root of 4 is 2 because 2 times 2 gives us 4. Square root of 9 is 3 because 3 times 3 gives us 9. When we look for a cube root, we want a number multiplied by itself 3 times, okay? Just as a refresher. So as I'm looking at my parent function for my cube root, we've got some x's selected for us here. And remember, we're multiplying that number 3 times. So let's start with 0 here. I'm going to start in the middle. I want the cube root of 0. Okay, this is an easy one. What multiplied by itself 3 times gives you 0? 0, yeah. So I would have the point 0, 0 on my graph. How about the cube root of 1? What do we say? So 1/3 would be this, right? If I added 3 1/3, I would get 1, but we want to multiply them. So over here, square root of 1 was 1, right? Because 1 times 1 gives you 1. Yeah, it'd be 1 again because 1 times 1 times 1 gives you 1. Remember, we're multiplying, okay? How about 8? How about the cube root of 8? 2, yeah. 2 times 2 times 2 gives us 8. And then what about 27? Yep, cube root of 27 is 3. So we would have the point 1, 1, we would have the point 8, 2, and we'd have the point 27, 3. Now let's take a look at the couple of values that I skipped here. Cube root of -1. Well, here's the thing. Yeah, this seems a little tricky. When we looked at square roots, we got something imaginary because a negative times the negative gives you a positive. If I try to take the square root of a negative number, I'm going to get something imaginary. But cube roots, I've got 3 of them, right? So this would be -1 times -1 times -1. Well, negative times a negative is a positive 1. But then I'm multiplying it by 1 more -1. That gives me -1. So I can have negative values when I evaluate a cube root. That's okay, because it's 3 things I'm going to multiply together. So I would have the point -1, -1. And then how about the cube root of -8? Yeah, -2. Cube root of +8 is +2. The cube root of -8 is -2. So -8, -2. So let's go ahead and plot these. -8, 1, 2, 3, 4, 5, 6, 7, 8, -2, -1, -1, 0, 0, +1, +1, +8, +2, And then that last one, 27 comma 3, is going to be off my page, so I'm not going to worry about that one. And then I'm going to connect my points. So as I look at my key features for this graph, I'm going to call that sort of center point or key point again. So our key point for a cube root graph for this parent function is 0, 0. And then our next points to help us with graphing are going to be those ones on either side. So to the left, I go out 1, down 1. So I've got -1, -1. To the right, I go out 1, up 1. So I get +1, 1. Because we can evaluate negative x values, we can take a cube root of the negative. I don't have any restrictions on my domain or range here. I'm going to go forever in both directions. So my domain is going to be all real numbers or everything from -infinity to +infinity if we do interval notation. And then my range will be the same thing. There are no limitations on what I can use for x or y here. So now with these parent functions refreshed in our brains, we're going to take a look at graphing things that are not just square root of x or cube root of x. Okay, so go ahead and turn the page for me. And we're going to take a look at the evens on page 3 for today. Just like with our warm-up problem, we've got some functions up at the top. I, for these, though, want to start with the description and see if those descriptions match any of the functions that we've got listed there. So first thing I want to decide, is this a cube root or a square root? So for number 2, cube root or square root? Square root, it only goes in one direction. This is a square root function. How is it changed from that parent graph? So remember, for the parent graph, our key point was at the origin. Our key point was at 0, 0. And then to get to that next nice point, we went up 1 and out 1. So the first thing I want to know, did my key point move? No. Did I change the stretch of this at all? Did I flatten it or stretch it up? Because to get to my next nice point, it was supposed to be up 1 and out 1. It's, yeah, sort of flattened. It's compressed. If I look to get to my next nice point, instead of up 1 and out 1, we are about halfway up. So I'm going to estimate this is compressed by a half. What it looks like to me. My next point out from there would have been out 1, 2, 3, 4 and up 2. And I can see that point that's out 4 from the key point is actually only up 1. So that's half that distance I would expect. Compressed by half seems like a good option here. So do I have a function that's square root of x, but compressed by a half? Do I see that represented here? Up at the top, D, yeah, half square root of x. How about number 4, square root or cube root? This is a cube root, goes in both directions. So this is a cube root of x function. I know that that key point, that center of my graph, was at 0, 0 for the parent function, was at the origin. Have I moved the key point on this one? No, it's still at 0, 0. Have I changed the stretch on it at all? Yeah, this is what I've changed. So I used to go up 1 and out 1 and down 1 and out 1. But now that nice point is up 2. So stretch by 2. Do I see an equation up top that would match this? cube root stretched by 2? C. And then number 6, cube root or square root. This is a cube root function, cube root of x. Have I changed the key point? Have I changed where that center point is? No, it's still at 0, 0. What have I done? It's flipped. Very good, flipped. What would I see in a function that would tell me this is flipped? A negative in front. Do I have that with any of my remaining functions here? A has a -2, but it's x -2. So we're looking for a negative in front, like how we had the 2 in front here. Doesn't look like I have a function that represents this. So for this one, we'll write it. So y equals negative cube root of x. Questions for me so far? Okay, we're gonna hop to page 4. We're gonna do some more practice with this same stuff. So keep those paragraphs in mind. You have them on page 2 if you need to flip back for reference, but we're gonna look at a couple more. So we're gonna look at 1 and 2 on the next page. So for number 1, square root or cube root? This is a cube root. If it goes in both directions, we're looking at a cube root. This is cube root of x. Have I moved that center point, that key point? Yes. How did I move it? It was at the origin. What did I do? I moved it to the left one. Okay. And then did I change the stretch of this at all? To get from my center point to my next nice point, it's supposed to be up 1 and out 1. Is that what I see here? No, it's up 2 and out 1. So I stretched this by 2. So before we look and see if we've got a match for any of these, I want to talk about what this should look like, particularly with this left by 1, with this translation on our coordinate plane. Okay, so we remember vertex form. I can look in parentheses with x and see where that x coordinate of the vertex will be, and it was always sort of opposite. So for our x squared, if I had x plus 1 squared, this meant I was to the left 1, and my vertex would be at -1. And then whatever the y was, let's say it was +3 here, that y just stayed the same. So in Algebra 1, when we talked about these, we talked about viewing that as a transformation, about shifting. And even when we sort of introduced that idea here in Algebra 2, we talked about how I could view this as a transformation, as a shift. We're going to take those exact same ideas as we're graphing and writing functions for these square root and cube root functions. So since I'm going to the left one, that means I would expect to see under my cube root the same thing that I would see here. So left 1 means my x value is at -1. So that means I want x plus 1 here under that root. And then the stretches and the compressions we already talked about. That means I'm going to want, since I'm stretching by 2, a 2 in front. So this should be my function. Do I have it as one of my options up at the top? C. Yeah, that's what I'm looking for there. So if I just had the function and I were going to graph, this would mean take your key point and move it to the left 1. And then in front, stretch by 2. Now let's take a look at number 2. For number 2, we have our graph here, square root or cube root. This is a square root. It's only going in one direction. So this is a square root. Have I kept that key point at the origin? No. How did I move it? Looks like up 6, I think. Let me double check. 1, 2, 3, 4, 5. I've got 6. Because the top line is 10. Your origin would be here. 1, 2, 3, 4, 5, 6. Up 6. So just like for our x squared functions, outside of x told me how I was moving up or down. It gave me the y coordinate for my vertex. I would have the same thing here. So this would tell me I would want +6 outside of that root. And then have I changed the stretch on this at all? Remember, my next point from the key should be up 1 and out 1. It is, so that means I didn't stretch or compress this. So I'm looking for this as a function for my options up at the top. Do I have that? B. Yep. Notice this is outside the root, right? Outside the root. If it were under the root, that would tell me to move left 6. So I have to be very careful as I'm looking at my functions. So this is actually equation B. Okay, we are going to stop there in our notes for today. What I would like you to do is go back to 3, page 3, and try the odds. Give those a try. Try the ones that we skipped. And then we'll talk about those tomorrow, sort of double check our work and keep working on our graph.